Modern enterprise data engineering is choking on its own infrastructure. As organizations scale, isolated data silos and fragmented processing pipelines inevitably devolve into tangled networks, overwhelming architectural limits. The root of this complexity lies in how we build cloud data estates, by stitching together disparate platform-as-a-service or PaaS offerings. We connect an orchestration tool to a storage lake, wire that into a data warehouse, and pipe the output to a separate business intelligence layer. The operational overhead of this fragmentation is significant. Engineers are forced to manage multiple identity planes, constantly duplicate data across isolated storage accounts, and track separate billing meters for every node in the topology. Microsoft Fabric addresses this overhead by delivering integration, data engineering, warehousing, streaming, and business intelligence as a single software-as-a-service analytics platform. Fabric places all workloads inside a single cohesive perimeter. Every engine shares one Entra ID identity plane, one storage layer, and one governance boundary. To understand how this consolidation works in practice, we have to examine the platform from the ground up, moving through its four strict structural layers: the hierarchy, the compute, the storage, and the network perimeter. Fabric's impact rests on this rigid structural boundary. By enforcing alignment across every workload, it targets the friction and complexity inherent in manual enterprise integration. The primary boundary of the entire architecture is the Entra ID tenant. Every data asset, workspace, and compute operation in Fabric exists within this single organizational boundary. Fabric dictates a strict four-level hierarchy to manage this environment. The tenant contains the capacity hosts the workspaces, and workspaces contain specific analytical items, like notebooks or semantic models. This structure replaces the traditional Azure model of provisioning specific data warehouse units, or vCores, for isolated services. Instead, organizations purchase a specific FSKU, which grants a fixed pool of capacity units, or CUs. These CUs act as a shared, liquid compute pool. The internal scheduler dynamically allocates this compute across different workspaces and workloads on demand, whether that power is needed for a Spark job or a SQL query. This line graph illustrates how Fabric manages high-intensity workloads through a mechanism called capacity smoothing. Compute usage is calculated on a 24-hour rolling average. When a heavy batch job causes a short-duration spike above the purchased CU limit, the system smooths that usage over time. This prevents immediate throttling of interactive queries or reporting layers, as long as the daily average remains under the threshold. By pooling compute into a single smoothed resource, organizations avoid compute fracturing. Resources no longer sit idle in one service while another is starved for power. Beneath that shared compute pool lies the storage foundation. This directory diagram maps OneLake, a single auto-provisioned instance of Azure Data Lake Storage Gen 2 that serves as the bedrock for the entire tenant. When you create a lakehouse inside a workspace, OneLake partitions the data into two distinct directories. The Files section holds unmanaged data in arbitrary formats, like raw CSVs or JSON. The Tables section is reserved for managed ACID-compliant data. To enforce platform unity, Fabric requires that all managed tables across the architecture be written natively in the open-source Delta Lake format, specifically Delta Parquet. Standardizing on one format is efficient, but bringing enterprise data into that lake has historically required heavy duplication. Fabric avoids this using shortcuts. As shown in this lineage map, shortcuts act as virtual pointers. They allow Fabric items to direct reference data stored in AWS S3, Google Cloud Storage, or existing Azure data lakes, creating a unified logical view in OneLake without copying any data. For operational data living in transactional systems, Fabric uses a different mechanism called mirroring. Mirroring establishes continuous, near real-time replication from external databases like Snowflake or Cosmos DB. It reads the source data and lands it into OneLake, automatically synchronizing it as Delta Parquet files. Because this data, whether native, shortcutted, or mirrored, funnels into OneLake, the OneLake catalog can act as a centralized metadata layer. It integrates directly with Microsoft Purview, applying lineage tracking and sensitivity labels across the estate. Combining OneLake, shortcuts, and mirroring reduces the need for redundant ETL staging layers. The data is simply exposed, standardized, and immediately ready for compute. This architectural map illustrates how different personas process that centralized data. Specialized workload engines sit between the shared capacity pool and OneLake bedrock. For the data engineering workload, Fabric utilizes managed Apache Spark clusters. These clusters draw CUs from the shared pool to execute Python, Scala, or R notebooks, scaling up dynamically as the code runs. For relational analytics, the data warehouse workload uses a distributed query processing engine. This provides full read and write capabilities, processing T-SQL commands against the Delta files in OneLake. Even without a formal warehouse, Fabric auto-generated a SQL Analytics endpoint for every lakehouse. This provides a read-only T-SQL interface over the tables, allowing SQL analysts to query data engineered by Spark developers. Streaming architectures require a different approach. For this, Fabric provides the real-time intelligence workload, powered by the Custo engine. Event streams route live telemetry into KQL databases. Custo applies columnar compression and partitions the incoming events, optimizing the data for high-throughput, low-latency time series queries. All of these workflows culminate in the Power BI business intelligence layer, which introduces one of Fabric's most significant innovations, Direct Lake Mode. This execution flowchart shows how Direct Lake changes BI performance. Instead of loading data into an in-memory semantic model, the Power BI VertiPack engine reads the Delta Parquet files directly from OneLake at query time. By reading the files natively, Direct Lake achieves query speeds comparable to import mode. Furthermore, because there is no data import, the visualization always reflects the current state of the lake without requiring a scheduled refresh. The separation of compute and storage allows Python engineers, SQL analysts, and BI developers to access the same data with their preferred tools, preventing format lock-in. Integrating external data requires securing the network perimeter. Because Fabric Compute runs on Microsoft-managed infrastructure, it cannot be deployed inside a customer's custom virtual network. This design necessitates a bifurcated security model. As shown in this network diagram, the rules for inbound access to Fabric are separate from the rules governing Fabric's outbound access to external data sources. The inbound pathway controls how users reach Fabric experiences, like the portal or a SQL endpoint. To secure this, organizations deploy an Azure private link inside their own VNet, mapping the Fabric URLs to a private IP address. Once the tenant setting to block public internet access is enabled, external traffic attempting to hit Fabric over the public web is denied. The outbound pathway requires a different mechanism. When Fabric Compute needs to reach an external, firewall-protected data source, it uses a managed private endpoint. Workspaces on an S64 capacity or higher spin up their Spark clusters inside a workspace-managed VNet. This network is isolated and managed by Microsoft. From inside this managed VNet, administrators can provision a managed private endpoint straight to the target Azure resource, allowing Spark notebooks to query protected databases without public exposure. For workloads like data pipelines and Power BI, Microsoft provides the VNet Data Gateway. This acts as a managed bridge deployed inside the customer's VNet to pull data back into Fabric. Note that the legacy on-premises Data Gateway agent is incompatible with Fabric once inbound private links are enabled. Finally, for creating shortcuts to firewall-protected ADLS Gen 2 accounts, Fabric relies on trusted workspace access. This utilizes a system-assigned workspace identity to authenticate against the storage firewall. Transitioning to a pure SaaS platform necessitates a complete evolution in network design. Identity-driven, managed endpoints replace traditional VNet peering. When the tenant hierarchy, the pooled capacity, the isolated network, and the specialized engines are combined, the goal of the Fabric architecture is realized. At the storage layer, the execution converges. Because the compute is pooled and the data format is standardized, an Apache Spark ML notebook, a data warehouse T-SQL query, and a Power BI Direct Lake report can all execute against the same Delta Parquet file simultaneously. This workflow removes the data pipelines usually needed to synchronize copies, as well as the storage costs for maintaining redundant staging tables. Fabric's utility comes from reorganizing how these engines are delivered. By enforcing rigid boundaries around identity, compute, and storage, it addresses the synchronization delays and management overhead inherent in multi-service PaaS architectures.